a workshop outside Berlin in the spring of 1918, a machinist lifted a peculiar hardware from a test bench. It was compact for an automatic instrument, barely 30 inches long, with a perforated metal jacket surrounding the barrel and a circular drum magazine protruding from the left side. The device had no official designation yet, just a functional description scrawled on the engineering drawings. Maschinenpistole, machine pistol. The name captured its essential paradox, a fully automatic system that used pistol ammunition rather than the powerful rifle cartridges that fed traditional heavy equipment. The timing of this prototype's appearance was no coincidence. By early 1918, the Great Conflict had entered its fourth year, and Germany's military strategists faced an intractable problem. Their units possessed some of the finest bolt-action rifles ever manufactured and deployed heavy systems that could deliver devastating sustained output. Yet in the confined spaces where much of the struggle's final phase was being staged, trenches, bunkers, fortified buildings, these tools proved inadequate. Rifles required too much time between shots. Heavy units required crews, tripods, and pre-positioned emplacements. What frontline teams desperately needed was a device that combined the portability of a rifle with the automatic capability of a heavy system, light enough for one person to carry into chaotic close-quarters engagements. Hugo Schmeisser, the designer, understood that this problem had no conventional solution. Traditional approaches to automatic function relied on complex mechanisms that locked the barrel and bolt together during operation, then unlocked them through intricate gas systems or rotating components. These designs worked brilliantly with high-powered rifle ammunition but added weight, complexity, and manufacturing difficulty, precisely what this emergency situation could not accommodate. Schmeisser needed something fundamentally simpler, a mechanism so straightforward that it could be manufactured quickly with available materials and machinery. The hardware on that test bench represented his answer, the world's first practical submachine gun. Its revolutionary simplicity came from a single insight, that pistol ammunition generated low enough pressure to make mechanical locking unnecessary. The entire system could operate through nothing more than the mass of a sliding bolt and the tension of a spring. When the first test procedure demonstrated the concept's viability, it validated not just a mechanical design, but a new category of equipment that would define infantry engagement for generations. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Hugo Schmeisser approached the MP18 project with the practical mindset of a man born into hardware manufacturing. His father, Louis Schmeisser, had designed equipment for decades, and Hugo had spent his entire adult life in the industry, first as an apprentice, then as a designer for Theodor Bergmann's company in Suhl, Germany's traditional center of toolmaking. By 1918, he carried the accumulated wisdom of that heritage, but also worked under constraints that would have seemed unimaginable just 4 years earlier. Germany's industrial capacity was deteriorating rapidly in the struggle's final year. Raw materials were scarce, skilled machinists had been reassigned, manufacturing facilities operated under constant pressure to increase output while working with substituted materials and simplified processes. Any new design had to account for these realities. It couldn't require rare alloys, ultra-precise tolerances, or lengthy production sequences. It needed to be manufacturable with the resources actually available, not the resources a designer might prefer. Schmeisser's engineering philosophy aligned perfectly with these constraints. He favored elegance through simplicity rather than complexity through refinement. Where other designers might add components to solve a problem, Schmeisser looked for ways to eliminate them. This mindset proved essential for the MP18's development. The device needed to deliver automatic function, but it didn't need to match the range or power of a rifle. It needed to be portable, but it didn't need to be comfortable for extended precision. Every specification was filtered through a ruthlessly pragmatic lens. What's absolutely necessary, and what can we discard? The decision to use 9mm parabellum ammunition exemplified this thinking. Germany was already producing this cartridge in enormous quantities for the Luger PS-08 sidearm, which meant supply chains already existed. The round's relatively low pressure compared to rifle cartridges meant the action could rely on simple blowback operation rather than complex locking mechanisms. This single choice cascaded through the entire design, determining everything from bolt weight to barrel length to rate of function. Schmeisser worked with a small team of engineers and machinists who understood that their goal wasn't perfection, but viability. They needed a tool that could reach frontline units before the end of the hostilities, something that could be manufactured in meaningful quantities despite Germany's collapsing industrial situation. The pressure wasn't merely professional, it was existential. Germany's leadership had staked enormous resources on a final spring offensive, and every piece of equipment that might tip the balance in close quarters movement carried strategic weight beyond its mechanical specifications. The core of the MP18's operation rested on a principle that seemed almost counterintuitive: letting the mechanism move during function. In traditional locked breech hardware, elaborate systems held the barrel and bolt rigidly together for the split second when gases reached peak pressure. Only after the projectile left the barrel did these mechanisms unlock, allowing the action to cycle. The MP18 eliminated this entire category of components through a mechanism called straight blowback, where the bolt was never locked at all. When a cartridge functioned in the MP18's chamber, the expansion pushed in two directions simultaneously. The projectile accelerated forward through the barrel while the casing pushed backward against the bolt face. In a locked system, heavy steel components would prevent that rearward motion. In the MP18, only the bolt's mass and a spring's resistance stood in the way. For the briefest instant, measured in milliseconds, those two forces balanced. The bolt's inertia and the spring's compression absorbed enough energy to keep the chamber sealed while pressure remained high. By the time the bolt actually began moving rearward, the projectile had exited the barrel and pressure had dropped to safe levels. This timing was everything. If the bolt was too light, it would begin opening while pressure was still high, causing catastrophic failures. If too heavy, it would cycle too slowly, reducing the rate of function and adding unnecessary weight to the device. Schmeisser's team had to calculate the precise bolt mass that would allow reliable operation with 9mm parabellum ammunition while keeping the hardware light enough for practical use. They settled on a relatively heavy bolt, about 2 pounds of steel, that would absorb recoil energy while cycling at approximately 400 rounds per minute. The mechanism's simplicity meant fewer failure points. The bolt was essentially a solid block of machined steel with a firing pin and extractor. The recoil spring was a simple coil wrapped around a guide rod. The trigger mechanism was straightforward: pull to operate, release to stop. There were no gas tubes to clog, no rotating bolts to jam, no complex linkages to break. Each simplification made the tool more reliable under field conditions, where mud, dust, and incomplete maintenance were inevitable realities. The perforated barrel shroud that gave the MP18 its distinctive appearance served a purely practical function, dissipating heat generated by sustained automatic function. Without any water jacket or heavy barrel to absorb thermal energy, the thin barrel would quickly overheat. The shroud created an air gap that provided insulation while allowing air circulation. It was an elegant solution to a problem that might otherwise have required much heavier components. Do you think this design choice was inevitable, or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The MP18's development proceeded through iterative refinement rather than dramatic breakthroughs. Early prototypes revealed problems that could only be discovered through actual use: springs that compressed too quickly, extractors that couldn't reliably grip spent casings, trigger mechanisms that wore prematurely. Each issue demanded a solution that balanced performance against manufacturing simplicity. Schmeisser's team couldn't specify exotic materials or ultra-precise machining when production facilities were already operating beyond their sustainable capacity. One persistent challenge involved controlling the hardware's rate of function. Blowback mechanisms naturally tend toward high cyclic rates. The lighter the bolt, the faster it cycles. But lightness also risked premature opening. Schmeisser's team experimented with different bolt weights and spring tensions, seeking the combination that would deliver reliable function without either cycling too fast, which wasted ammunition and reduced controllability, or too slow, which might cause feeding malfunctions. They eventually settled on a configuration that achieved roughly 400 rounds per minute, fast enough to deliver effective automatic output, but slow enough to remain controllable in short bursts. The magazine system presented its own complications. The trommel magazine, the snail drum magazine borrowed from the Luger artillery sidearm, held 32 rounds and fed from the left side of the device. This magazine had been designed years earlier for a very different application, and adapting it to the MP18's higher rate of function required modifications to the feed lips and spring tension. The drum's helical design, where cartridges spiraled inward toward the center before feeding into the device, created complex spring geometry that sometimes resulted in interruptions. But abandoning it would have meant designing and manufacturing an entirely new magazine system, a luxury Germany's industrial situation couldn't support in 1918. Testing protocols focused on the conditions the tool would actually face: extended use sequences that heated the barrel to operational temperatures, exposure to mud and water that simulated trench conditions, rough handling that tested component durability. These weren't precision trials, but endurance tests. Could the hardware function for hundreds of rounds without critical failure? Could it work after being dropped? Could a user clear common interruptions without tools or extensive training? Each question demanded practical answers that could be verified through physical testing rather than theoretical calculation. By the time the MP18 received official approval for production, it represented not the perfect automatic device, but the viable one, a tool that could be manufactured with available resources, maintained under field conditions, and employed effectively by ordinary personnel without extensive specialized training. Its specifications reflected compromise at every level, but compromise guided by a clear understanding of what mattered most: delivering automatic capability in a portable package that could reach units before the conclusion of the conflict. The most revealing detail about the MP18's development wasn't its innovative blowback mechanism or its compact design. It was the magazine. That peculiar 32-round helical drum protruding from the device's left side told a story about wartime engineering that no technical drawing could capture. The trommel magazine hadn't been designed for the MP18 at all. It was created years earlier for the Luger P08 artillery sidearm, a specialized variant intended for use where a standard capacity proved insufficient. When Schmeisser needed a high-capacity magazine for his new tool, he didn't design one from scratch. He simply adapted what German industry was already producing. This decision revealed the profound constraints under which the MP18 was developed. In 1918, Germany's industrial infrastructure was struggling under the combined pressures of material shortages, labor depletion, and infrastructure damage from 4 years of total mobilization. Copper was scarce. Steel quality was inconsistent. Machine tools were wearing out faster than they could be replaced. Under these conditions, any new design had to maximize the use of existing production capabilities and minimize new manufacturing requirements. Creating a novel magazine design would have required new tooling, new dies, and new production sequences, investments that the deteriorating industrial base simply couldn't support. The trommel magazine itself was a masterpiece of complex engineering, almost paradoxically intricate for a device designed around simplicity. Inside its circular housing, a coiled spring drove cartridges along a helical path that spiraled inward toward the center feed tower. The geometry was elegant but unforgiving. Small variations in spring tension or cartridge dimensions could cause interruptions. The magazine required careful loading in a specific sequence and didn't tolerate rough handling or exposure to debris. In many ways, it represented exactly the kind of complexity Schmeisser had eliminated from the device itself. Personnel who used the MP18 in the field quickly identified the magazine as the hardware's primary weakness. It jammed more frequently than the device itself malfunctioned. It was difficult to load under stress. Its circular profile made carrying spares awkward. Within a year of the cessation of hostilities, designers were already developing simpler box magazines that would eventually replace the drum entirely. The MP18-2, introduced in 1920, featured a straight box magazine holding 20 or 32 rounds, a configuration that would become standard for such equipment worldwide. Yet the trommel magazine's very inadequacy illuminated an essential truth about the MP18's creation. This tool was never intended as the definitive solution to automatic design. It was an emergency expedient, assembled from available components in the desperate final year of a losing effort. Its success came not from optimization, but from pragmatism, from Schmeisser's ability to identify what could be built with the resources at hand and engineer a functional tool within those brutal constraints. The MP18 arrived too late to influence the outcome of the Great Conflict. Germany manufactured approximately 35,000 units before the November 1918 armistice, and most never reached frontline units before the struggle ceased. Yet this timing, paradoxically, amplified rather than diminished the hardware's historical significance. Because it appeared at the conclusion of the hostilities, it avoided being forever associated with a specific incident or tactical doctrine. Instead, it became something more influential, a proof of concept that demonstrated these devices were viable, manufacturable, and tactically useful. In the decades following the conflict, virtually every nation that developed similar hardware did so by studying the MP18's principles. The device's straight blowback operation became the dominant mechanism for equipment in this category. Its use of pistol ammunition established a standard that persisted for generations. Even its mistakes, particularly the problematic drum magazine, taught valuable lessons that shaped subsequent designs. Various global models all descended conceptually from Schmeisser's 1918 design, even when their outward appearance differed dramatically. The MP18's influence extended beyond mechanical design into tactical doctrine. It forced theorists to reconsider the relationship between output, portability, and effective range. Traditional doctrine assumed that units needed to engage targets at hundreds of meters. The MP18 demonstrated that many situations occurred at distances where pistol ammunition was entirely adequate, and in those scenarios, automatic capability mattered more than extended range. This insight gradually reshaped tactics throughout the mid-20th century, leading to the development of versatile modern systems. What makes the MP18 story particularly compelling from an engineering perspective is how thoroughly it vindicated Schmeisser's philosophy of simplicity. More sophisticated designs appeared in subsequent years, tools with finer machining, better materials, more ergonomic features. Yet none proved fundamentally superior to the basic principle Schmeisser established: a heavy bolt, a spring, and pistol ammunition. The mechanism was so elegant in its simplicity that it required no meaningful improvement. Later designs refined the execution, but the core concept remained unchanged. The hardware also demonstrated an important truth about engineering under constraint. Perfection is often the enemy of completion. The MP18 was flawed in numerous ways. The magazine was problematic, the sights were crude, and the overall ergonomics were barely adequate. Yet it succeeded because Schmeisser understood that a functional tool produced in time was infinitely more valuable than a perfect tool that never reached production. This mindset, this willingness to embrace pragmatic compromise in service of achievable goals, became one of the most enduring lessons. In workshops and engineering schools today, the MP18 serves as a teaching example of how to design under extreme constraint. Students study it not because it represents optimal engineering, but because it represents realistic engineering, the kind that acknowledges limitations, works within them, and still achieves revolutionary results. Hugo Schmeisser's 1918 creation proved that transformative innovation sometimes comes not from having unlimited resources, but from having the wisdom to make the most of what's actually available. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.